So anyway, here there are like two things. So there is this thing about impredicative polymorphism, and I would like to tell you a bit about what it is and why we consider this somehow important. And then, well, what happens is that if you want to design a language which supports impredicativity, you run into problems. So after some time thinking very hard, we came to a solution, and this is the solution about what we call guardedness. And well, I would like to show you a bit of the solution, and hopefully we got somebody working on implementing this for GHC. So sometime we might send whatever a pull request is called in Fabricator, which is this weird system they use to put the code together. So anyway, what happens here is if you get some Haskell code like this, where you have something like function head, which works for different types, and that we indicate that, and I'm going to be very explicit about that, we indicate this with the word forall. So the function head works for every possible way you decide to change a to. So it works as a function from list of int to an int, from list of bool to a bool, from list of maybe of bool to maybe of bool, whatever you choose. So when you actually get a list of int, the compiler has a job to do, which is to find out what this a should be. So when you have head of x's, it actually needs to find out, wait, the a in head has to be replaced by int in this case, and that's what we call an instantiation. So the a is instantiated to int. Now imagine I have these weird types. So head is still the same, but now my list is a list of functions which are themselves functions with a forall. So you can take one of these functions, so you can grab one of these functions and then instantiate v to whatever you want and apply it to a value. So and this can be a list of them. So you can have a list of different functions with this type, and for each function you can decide to instantiate the v to something and apply it. So in principle it looks like, I mean, what's the problem? You know, you get this thing, and if I want to get head of x's, then well, I need to make my a equal to forall b to b. That's how I do this. So the problem here is that this kind of instantiation is special, and it's called impredicative, because the a is given a value which contains yet another forall. So you are taking something from a forall, one of these variables, and replacing it by something which is a forall again. And we call it impredicative instantiation. I think this comes from some philosophy or some logic and mathematics, but the name has long lost its original intention. We just call this thing impredicative anyway.
Different than existential, right?
Yes. So this is actually like a universal type. So it tells you, no matter what you choose for a, I promise that I will work for you. An existential type is reverse. It means I only work for a type, but I won't tell you. So it's like it's in Haskell it's a bit confusing, because when you want to create an existential type, you wrap it into a new type which has a forall inside. And this works as an existential. So the syntax is kind of doesn't tell you this is an existential. You still use forall. So why you would ever like to do this? So I mean, this looks very kind of, you know, why would you like to have a list of functions with this type, which by the way will only be identity functions in Haskell? So it's kind of a very stupid thing to do. So actually, if you start writing more complex code, you come to this problem. So in Haskell, we have this monad called st, which allows you to have mutable variables. But they are built in such a way that this block is encapsulated. So at the end of the day, you call run.st, and this sort of purifies your code. It makes sure that your mutability is located only here. And if I cannot observe this mutability from outside, this is still pure. So this, you can see this in the type of run.st. So you get some operation in the monad st, which generates a value of type v, and then this will give you the value v, and this is all pure and nice. So by the way, this is actually quite nice if you need to implement the imperative algorithm in Haskell, but still you want to be pure, but use mutable variables, because maybe the algorithm is explained in that way. That's a good way to do this. Okay, but the important thing is that you will notice that there is like a forall inside another forall, and this is part of how the library is built. And I won't go into details, but this is what allows st to control the location of the mutability. So when you do this, people usually write this pattern. They use this special type of application that Haskell has, which is the $, and they say, okay, apply my run.st over a monadic computation, which is my whole mutable variable thing. And you really see this into code. But if you want this to work, that means that the a in the $, has to be instantiated to this forall as STSB. So again, this is a case of impredicative instantiation that actually happens in real code, and people tend to write this all the time. And this is actually so common that even though it shouldn't work, GHC includes a very special rule only for $, to make this work. So there is like a hack in the compiler to make this work. So that's, but you know, there shouldn't be hacks in a compiler. Another place where you find this this kind of thing becomes useful is if you have the lens library in Haskell. A lens is defined by this big thing. You don't need to understand why this is a useful thing, what is a useful representation. What is important is that there is a forall there. So a lens is somehow some kind of polymorphic thing which allows you to turn functions into some other kinds of functions. And then there is a whole vocabulary of what you can do with these lenses. And for example, you can find this inside function, which essentially says, okay, I have a lens, and now I want to apply this lens, but into a bigger context, which is represented by this co-representable P. So it's, imagine you have a lens which works over your person things, and then you want this to work on maybe of this person, so you can just like say, okay, apply this lens inside this other co-representable functor. Again, what is important is that if you expand lens and lens, you will get a forall and a forall. So you really want all these foralls to be able to be manipulated in the compiler, because they are useful in certain things. So of course, just take this with a grain of salt. These kind of things are complex operations. It's not that code you write every day. But if you start writing lenses, for example, it's not very hard to come into a place where you would really need to have this. So now you cannot do that. So this won't work in GHC right now. So people have come with some workarounds for this. So first of all, you can just be very explicit about instantiation. So if you tell the compiler, this is how I want you to instantiate this thing, then it says, okay. I mean, if you tell me, I have nothing to think about, so I can just check. So you do this with this @ symbol and saying, okay, I want head over this specific type. Also, if you look at the lens library, what you can do is to somehow hide the fact that you have foralls by using a new type. So this should be new type, not type. And then this is actually something you find in the lens library, because you cannot have a forall here they just put it into a new type, which hides this, because this a lens no longer has a for all. It's just a completely new type. But it has the problem that now when you want to use the inside function, you cannot use your lens directly. You have to wrap it into this new type yourself. And this wrapping and unwrapping has, well, takes some time to do. So in general, I mean, impredicative types are quite hard if you want to use this all the time. And I will show you actually the reason why it's hard, why I start talking about this. So just to be clear, people have come with many solutions. So some people say, okay, if you want to do this, just annotate everything, because otherwise it's too hard, and you better be explicit. Some people decided, okay, we need even more complicated types, and there is something called MLF, which says, okay, we can have types which have like greater than and things like that. But the problem at the end of the day is that whatever you want ends up becoming very complex. So I want to give programmers something which gives them power enough to have all these use cases covered, but it's not so complicated that they cannot explain what's going on. I want the errors in the compiler to be understandable, and that's sort of the trade-off you want here. So, and another problem is that, okay, even though we tend to say, okay, everything is lambda calculus and everything is going to be fine if you use lambda calculus, that's far from true. So if you use in Haskell, if you use GHC, you also have all these type classes, type families, GADTs, promoted type, you name it. If you would like to do this in Scala, I guess you would have all kind of subtyping and other kinds of types. I'm not an expert in Scala, but none of the real languages, none of the mainstream languages we use is really lambda calculus. It's lambda calculus plus other things. And we don't want to remove all the other things to get our impredicative types in. So the goal of this is how we can get impredicativity for GHC, so for Haskell, in such a way that it's simple. And that means that I can tell you a specification which is simple enough, so you can understand why your program works or is not type checked. But still, you can have a good expressiveness, so it still covers all the more common use cases that people have. In particular, you can use this run st $, which everybody is using in the wild. And furthermore, you don't lose any other thing that GHC already had. So you don't lose type classes, you don't lose roles, you don't lose GDTs, and all of that. So question up to here. No? That meant? Okay. You're not sleeping?
Very clear.
I think. Okay.
More about the MLF?
Yes. So the idea of MLF is that so imagine the function like constant, which usually would have a type a to b, but actually you could also think that it actually gets an a and then produces a type in which then you can choose the b. So MLF is takes everything in which you can choose again and puts this with this greater than thing. So the type of const here is actually, you give me an a and I will give you a b, and by the way you can turn the b into this for all c to c. So this the fact that they have all these things very explicit make it possible to sort of know more about your code at the expense of your types. Is no longer something simple like this. You have to write them in that way, and actually you need yeah, that would be no, it should be it says const too, but I'm not showing it here, but actually it's not enough to have this greater than. You also need like greater than or equal and equal, because sometimes you really need to fix things. Okay, so let's try to see the difference and try to figure out why this impredicativity I was claiming it's hard, but I haven't shown you a case where it's hard. So imagine I have this case. Okay, I'm showing it before. So I have head, and I have to choose what A is, and I have a list in which I tell you that has this type. So somebody told you this type. So it seems that in this case it's not very hard. I mean, you just compare and say, oh yeah, it's a list of A's, and then you need to apply to a list of for all BB2B. So A must rather be for all BB2B. So this is a case which is fine. This seems to be fine. On the other hand, if you reverse the order, well, we have this singleton which gives you give it a value and creates a list with this single value. If you try to apply single to ID, you actually have a problem, which is you don't know what type to give to this expression. Because you can say, okay, maybe the programmer wants to have a list of polymorphic functions inside. Or maybe the programmer wants to have the polymorphism outside. And I will show you why this makes a difference. So if I have the first case, so if I have a list of for all B2B, I can go through the list and choose every B independently. So I can go and say, okay, I get the first element to the list and I apply this to a Boolean value. And I go to the second element of the list and apply this to an integer value. And that's okay, because every time I get an element, I get the for all, so I get to choose once again. But in the second case, where the for all is outside, I only have one moment in where I can choose. So I choose the B, and then every element inside has the same B chosen. So I can, if I choose B to be bool, then all my functions turn into function from bool to bool. So I cannot apply one to int and one to bool. So in some sense, you can. This is a bit more powerful than the other below. But the problem here is we don't really know. So we don't really know what's the intention of the programmer. And that's problematic, because that means that we cannot infer types well. Because the whole point of type inference is to, you don't have to write because we know what you are saying. But if we don't know what you are saying, our inference system breaks. So the problem actually, the solution actually is kind of simple. So what's the difference between this case and that case? The difference is that the arguments in the first case, in the case of head, appear inside of a list. And because they appear inside of a list, when we compare with another list, we can just check one with the other and figure out what A has to be instantiated just by comparing what is inside of the list. But every time we have a variable like this, which has no constructor outside, which appears just naked or unguarded, then we don't really know. We always have these problems. So do we put the for all inside, or should we put the for all outside? So that's the key intuition here. What we are going to do is to say, if you are free to choose whatever you want for a type variable, if this type variable appears at least once in one argument inside of constructor. And why you can do this is because, for example, in the case of a list, if you know that you want a list of some t's instantiated to a list of some rows, then it has to be the case that this one is equal to this one. And before the Scala people kill me, yes, that's because in Haskell we don't have variance or anything like that. So we can do this. So that's also something which is important. In a Scala, this won't really be like this, because you would say list of t's is an instance of list of rows. That only implies that t itself is an instance of list of rows because of the variance of lists. But here we can do this, and because we have invariant in every data type in Haskell, then we can just take advantage of it. But on the contrary, if the type variable only appears without any type constructor, we are going to enforce, we are going to say, you can only be instantiated with something which has a type constructor on top. So for example, if we have single ID here, we are going to disallow this thing, because that would mean that the A is instantiated with something with a forall. But we said you cannot do that because your A never appears inside of a constructor. So that leaves us with only one possibility, which is this one. So we have sort of decided among the two possible choices, which is the one you want to have.
But isn't A, B, and beta, they can be, like in the second one, we can replace beta with B.
Yes, but the forall will be outside, so you will get this at the end of the day. So you can. The problem was which one of these you choose, and the solution is you cannot choose this because I'm not allowing you to choose forall B, B to B as an instantiation of A. So this is the only possibility that you have, to get a B and put the forall outside.
Will this break any code?
No, it won't break. Well, there is no code which uses impredicative types now, because it has been, they're known in, so Haskell, GHC used to have an impredicative type extension, but I think 2 releases ago, it was so broken that they removed it, and nobody complained, which I take as a symptom that actually nobody was using it because it was broken. So now, I mean, it's like a green field. Nobody's using this because it's new, so and it doesn't break any of your normal Haskell programs. So something which I started to mention about lists in a Scala is that, well, in Haskell lists are invariant in the type variable, but in Haskell they are invariant, but in Scala they have some variance, so they are covariant. But actually, in Haskell, there is only one type constructor where you still want to be a bit co and contravariant, and that's in the case of arrows. So you sort of want to be the case that if I have this function, which sort of says you give me an int and I will give you a function which gives you back a new function which is similar to identity, that if I want to use it in a place where they demand me something of this form, I can just plug this function inside of here. So that means that I have to take care that when I have an arrow, I can instantiate a bit of the foralls here, and people actually take advantage of this kind of things in Haskell. So that's also a reason why you want to do this. So actually, for most of the cases, you don't have to do anything. This takes care of the same rules. Take care of this, and sometimes, unfortunately, and this is a problem still with the technique, you need to expand your thing like this. So if you have this, so some f which requires you this type, and then you want to pass a g which has this type, and they look very similar, just you have different moments to choose what a and b are, but in principle they are the same function. You cannot do this. You have to expand the x, because now you are allowing to make the choice a bit later. So sometimes you need to play this trick here and there. But anyway, this is also kind of a good thing, because right now in GHC this transformation is done automatically for some complex types, but this is not really sound because it changes the laziness behavior of your code. So if G throws an exception and you turn it into this will no longer throw an exception, because this This is just a function. It will throw an exception later. And the same happens for laziness. So this is something which you don't really want to do unrestrictedly. And then there is the last problem, which is the problem that you won't find in a Scala because of variance, which is what if I need some function of elements which implement equality, and I just have a list of functions which happen to implement order. So they are, and in Haskell, implementing OR implies that you implement EQ. So it looks like, you should be able to turn this thing into this thing automatically. But actually, you don't want to do this. Because if you were to turn this thing into this thing automatically, well, it might look automatic from outside, but actually there is work to be done at runtime. If you want to turn this function into this function, this list into this list, you have to traverse all this list and turn every call in which you use this OR thing into now one which extracts the dictionary of equality from the dictionary of OR and use only this. So there is really some work to be done there. It looks like it's magical, but if you want to have this in Haskell, you don't really have magic. You have some runtime penalty. So it's not very clear that you want your programs to suddenly have runtime penalties just because you are using some strange types. So this is just a bit to say, OK, what we are doing seems a bit weird and a bit restrictive, but actually, most of the restrictions actually have a cost. And maybe you don't want this cost, and it's better to be explicit about these costs. So anyway, I mean, as I said, this is a technical thing, so I get to write my theorems. So this is very long. But what this is essentially telling you is that, well, you don't lose something which is very nice that you have in Haskell, which is that every expression has what is called a principal type. And just to give you an idea of what that means, so imagine you have the empty list. So the empty list may have, you can say it's a list of int, or you can say that it is a list of bool, or you can say that it is a whatever list of maybe string. So it looks like, OK, there is an expression, and I have the same problem as before. I have many types to choose. So inference won't work in these kind of occasions. But there is always a type which encompasses every other type that you can have. So in this case, that would be for all A, list of A. And this is what is called the principal type of this expression. It's a type which you can use to get any other possible type of the empty list. And this is a very useful property you don't want to lose. And the system, as I shown, actually keeps this property. So this is what the theorem is saying, but the idea here is we rather prefer to have no type than two types. So instead of making a guess, if we cannot make a guess, we say we cannot continue. But in the other cases, if we say, yes, your code is OK, that means that we can always find this principal type, which is the least restrictive type you can give, which you can then instantiate to everything you want. OK, so that's about how the intuition works. And I would like just to give you a sneak peek of how actually you can implement this kind of things in a compiler like Haskell. So right now, I think there was a tutorial on the first day. But as a very fast summary, so a compiler like GHC works with your code in two phases. So essentially, it goes first by gathering a lot of constraints, which are like equations among the types in your program. And then in a second phase, it tries to solve all the equations that it has. So for example, if you have an expression like f of e, so the function f is applied to e, well, regardless of what the type of f and the type of e is, you know that the type of f must be equal to the type of e. So the type of the whole function must be a function type, the argument must be the type of this argument that you are given, and it returns some other type R. So this is, if you like mentally change the symbol they use in GHC for an equality, this is just like an equality between types. And it generates one of these things for every part in your program. And then it just gets a whole bunch of equalities, and then it's like in high school, you just have to go and try to replace one by the other until you get a result. And if at some point you get something like int equals bool, that's when you say, oh, your program is wrong, because int does not equal bool. And yeah, that's essentially what it does. So it's, I mean, of course, you need to, this is a very high level description of how both generation and solving work, but this is the general idea. And the other thing which it has to do is, if you have something like head of x's, the type of head has a forall. So what it does, so okay, we said that it needs to find out what this A is. So what it does is it generates a new, a new name that it's not used anymore, like a new variable, and it replaces the A with this thing. So I usually use the Greek letters for those, but you can think like if you had x's, what you will get is, okay, this type with a new variable x, which have just invented, has to be equal to the type of x's to whatever result we get. And this will tell us, for example, that x's has to be a list, and that the result has to coincide between these two x's, and so on. So this is essentially how the compiler works out what are the types in your program. Okay, yeah, and this is the same thing I wrote here, but in the screen. What we do now is, okay, now every time I find head, I just go on and replace this thing by new x's. But if you want to keep this impredicativity working, you cannot be so eager doing this. Instead of that, you have to introduce new constraints which say, okay, I don't know what any of those type, sigma and mu, are, but I need to have a solution such that my sigma can be turned into my mu. So that you can choose some variables and then you get a mu back. And actually, but by how all of this set up, we will know that the type on the right hand side is not going to have for all. So this is something that is just something that happens in the system. So now something like head x's doesn't really include these new variables. You just remember that this for all, at some point you will have to tell me how it's turned into this new type of form alpha to alpha, and actually that this type, the type of the argument, can be turned in the type that you are required by head. So the idea is, before you just said, okay, these two things have to be equal, but now you are delaying this decision a bit more, because, okay, if you have an argument to a function, it doesn't, so the argument doesn't have to be equal to the argument required by the function. It only has to be the case that the argument can be somehow turned into the thing that you require. So if you give me like an empty list and I require a list of int, well, it's enough if you can turn the empty list into a list of int somehow. It doesn't have to be exactly equal from the very beginning. And this already takes you quite far, but yeah, I don't want to go into the details, but this is not enough once you introduce lambda expressions. You also need to remember that at some point you can also introduce for alls yourself. But yeah. So the nice thing about this system is that actually, even though all these weird constraints with instantiation constraints are introduced, we were able to prove that at some point they are all removed. So this is just like as an intermediate phase, you generate these things, and then everything is sorted out, and then you get back again a list of equalities. And then once you get your list of equalities, you are back into your normal Haskell territory. So GHC can continue doing their business. And this is kind of a nice thing. You can get this system and introduce it into some other thing which just needs equalities, because you know that at some point everything is going to disappear and you will get back only a bit of equalities. And this happens even if you have type classes, GADTs, whatever extensions you want to shoehorn there, it still keeps working. Yeah, so just, I mean, if you want to know a bit more names, so this theorem on top is what I was saying. So you know that at some point you will only get equalities, and there is a theorem by two French researchers, Potier and Remy, which says that there is actually an algorithm to solve any equality problem you pose between types. And the fact that you have this and this thing, that means that you have a complete algorithm. So you will never get into a program in which you say you don't know. You only get to a program which I say it's not right or it's wrong, which is what's the point at the beginning. I just don't want to be stuck saying, I don't know, programmer, just, I don't know. That's like the worst thing I guess you can get as a type error. So I'm at the compiler and I don't even know. So go fix it yourself without my help. So that's a good thing. So just as a summary of all of this, so doing this and still I hope it was not too technical. The idea is that we want to get impredicative types and they're useful, but we also want to make them simple. And I think that this rule, which is, okay, you can do whatever if you know that there is a constructor somewhere, is simple enough to be explained to a programmer and sort of have a feeling that this program should or should not work. At the same time, and this is something I cannot show you really with theorems, is that the system is quite expressive, and we try to check that this is the case by taking all stackets. So essentially, all packages that the community has put into this public repository of Haskell packages, and go on and compile all of them, and almost all of them compile, which is quite interesting. And sometimes you just need to do it exponent, so you need to change a g into lambda x g of x. But this is like, there is an error which tells you this, and I think we had to change like 15 packages out of like thousands of them. So I think that's a good balance. And the nice thing is, as I said, it works in G with all the extensions of GHC. So I hope that by next year we will have something which allows you to have this kind of impredicative type and still allow you to have all these fancy GHC features. So that's all. If you have any question.
It would be an extension. This would be an extension also that people would turn on.
Yeah, I don't think people would like to have these things in their code by just, appearing randomly and just having weird types appearing at any point. Yeah.
I don't have a question, but I wanted to add something interesting. I was working on the C++ compiler and implementing templates, and we ran into problems within type inference and stuff. And the C++ code that was trying to figure this out, we had called it dymto. Do you mean this one?
What?
The CP file that we had, which was computing this, it was called dymto. Do you mean this one?
dy?
Do you mean this one?
Ah.
It was like one of the hardest piece of code that I ever written in my life. Oh my god.
Yeah, I'm working on a C++ compiler. Implementing templates looks like a lot of pain, even without the problem.
And with type inference with generic types, that was quite a bit.
Good. Okay, then I guess we can go have some coffee and some cookies.